Well, you've already met him, but I'm going to introduce him briefly. This is Ralph McNutt. He's at the Hopkins University Applied Physics Lab. He's the project scientist of MESSENGER, which is the other end of the solar system, and he's a co-investigator on New Horizons and has been a co-investigator on Voyager, and he has been involved in a lot of the interstellar probe and interstellar medium discussions, including helping define the heliophysics objectives as part of the decadal activity. And so I've asked him to review the previous interstellar probe studies.
Thank you. So you know, it's interesting to go back and sort of look at the history of ideas, because that gives you a little bit of an insight into kind of where we're going, especially given that in the space business, typically just if you come up with the idea for a mission, it takes a little while to actually get it to fly. And this turned in to be an interesting hunt, trying to go back and find out where the beginnings of some of these things actually were. Oh, great. Let's see here. Let's try. There we go. So it's not about interstellar travel, and Freeman Dyson actually gave a really nice introduction to this. And the good news about actually having your slides with you before you give your talk is you can change things like putting Atlantic mode in the title of the slide just before you get up. And you know, I was going back and looking, and at least the first thing I've been able to find was for sort of a mention of this by some of the credible people was Robert Goddard's Great Migration, which he penned on the 14th of January 1918, stuck in an envelope, sealed the envelope up, and said it ought to be opened by somebody at something like the Smithsonian, but only by someone who was a great optimist, because this was talking about what we might have to do one day when the sun decided that it needed to go nova and we had better be someplace else. Tsiolkovsky, of course, had penned some things as well. Friedrich Zander actually had, he didn't write a lot, but he gave a lot of talks, and he talked about going away for millions of years and using time dilation with relativistic speeds and then to come back. There's a lot of other stuff that people have talked about. Eugene Sanger talked about photon rockets in the 50s and the 60s as ways maybe of being able to do interstellar missions. And Sebastian von Herner, of course, talked about what the ultimate limits to space travel might be. But that's not what I'm going to be talking about. I'm also not going to be talking about the Polynesian mode, colonization. Actually, J.D. Bernal, in The World, the Flesh, and the Devil, back in 1929, talked about maybe us all needing to go to another place, sort of in the spirit of Goddard. And of course, there have been other people that have written about this as well. Stephen Dole in the Rand Report back in '62, all the way up through Bob Forward in '76. So, you know, trying to go back and find out where all this notion of an interstellar probe started, and there may be some of you in the audience that can help fill some of this in, but about the best I was able to do was to locate this meeting. This is the 17th AAS meeting in Seattle. This was in June of '71. This is the other AAS, the American Astronautical Society, not the Astronomical Society. And there was actually a whole series of talks about the scientific and technical bases for solar system escape missions. And sort of the predominant one was penned by Alex Dessler and by Park, and talking about putting this in the context of the forthcoming flights of Pioneers F and G, translation Pioneers 10 and 11, because this was before that they had launched. And they talked about the idea of looking out and seeing what you might be able to do and what we might ought to look at, such as how that the solar wind forms a special region of interplanetary space called the heliosphere, which of course Ed Stone talked about our modern notions of that this morning. And it was sort of, as far as I can tell, Alex apparently is the one that coined this term in a Reviews of Geophysics, Space Physics and Geophysics article back in 1967. And Alex Dessler called on that in terms of talking about the particular ideas that were formed within this conference. And I found it interesting, the three main references he gave, one was to Leverett Davis, of course was here at Caltech, and talked about the magnetic bubble in the solar wind, and this was back in a paper in 1955 in Phys Rev, a paper by Clauser entitled The Aerodynamics of Mass Loss and Mass of Stars. This was an AFOSR technical report, 1960. And then, of course, Alex's own paper from 1967 about the solar wind. And indeed, this is the concept that he showed, and you can compare this with what Ed mentioned this morning, and talking about the possible interaction and configuration sketched out and what that we might want to find out by having a solar system escaping spacecraft. Now, it turns out that really the Grand Tour was the grand motivator for thinking about the interstellar medium. And Ed talked about Gary Flandreau and his realization that the Grand Tour is something that one could fly. Of course, started out with all of that in the 1960s. There was work done at JPL looking at what you could do with a spacecraft to do that. And of course, turns out that that notion was then extended to solar system escape within the context of these 71 papers. And one of the articles was by Sergeyevsky, and again, this was writing in 1971. And he noted that as long as the spacecraft systems function, they could sample data on the properties of the outskirts of the solar system and their interactions with the interstellar medium. The idea of where you would go once that you could actually get past the solar system. And one of the things that was noted, and Alex had picked this up, was that the direction of the Grand Tour spacecraft would be good for such studies. And it was really a great time to be doing this. The sketch here shows where the various places are that you could actually aim the spacecraft as you're going out. This is from Sergeyevsky's paper. Noted that the immediate conclusion is solely that the Grand Tour spacecraft escape from the forward part of the heliosphere is not only possible but unavoidable, whereas Pioneer F and G are denied this opportunity. Well, of course, Pioneer 11 ended up going in the same direction basically because of doing a retrograde encounter with Jupiter and then encountering Saturn. Pioneer 10 going down the so-called heliotail. And, but again, all of this motivation was going on in this time of the early 70s. There were a lot of other discussions at the 71 meeting as well, and it took me a great deal of digging to find this silly volume because no, it is not online. Yes, libraries still are really important that have books and journals in them. I'm sorry, but cost-cutting measures about getting rid of things because everything is electronic just really doesn't work that way. There was a lot of talk about scientific explorations of near-stellar systems, again, scientific goals. An interesting paper called The Ultraplanetary Probe by Kraft-Ehricke, and some of you may know about Kraft-Ehricke. Of course, he was the person that really was involved at Convair Corporation in bringing to fruition the LOX liquid hydrogen rocket engine. And he wrote quite a bit about this idea of really getting out of the solar system fast by doing a retrograde encounter with Saturn and being able to use that to advantage along with a powered flyby also close into the sun and getting out very rapidly. Of course, there were some issues with some of the rocket engines that were needed and some critical maneuvers, but nonetheless, this was at an early point. I also found it interesting, there was a paper by Jaffe and O'Riordan from talking about extended lifetime design in radioisotope thermoelectric generators, because there was the realization that if one was going to do some sort of an interstellar mission, that one was going to have a very long-lived power supply, kind of like the ones that have lasted for 37 years now and counting on Voyager 1 and 2. So after that, one of the things that was done by the agency was to put together a thing called the Outlook for Space Study. This was done during 1975. The book actually came out in January of '76. And one of the items that was mentioned was item 1069, which was also embedded in a very rather primitive version of what we'd call a traceability matrix these days. For those of you who've had the misfortune of having to write NASA proposals for missions, and they noted that a small spacecraft with a particles and fields instrumentation launched in 1980, by a Titan Centaur plus a high-performance upper stage is on a trajectory escaping solar system in general direction of solar apex. If mentioned launched in the late 80s, electric propulsion, solar sailing, and or Jupiter swing by could be used to reduce the transit time to the heliospheric boundary, mission duration 10 years or more. But anyway, it was within the mix at that time coming together about, what would be needed for some sort of a mission, what might actually make sense. Now, I've been talking a bit to Lou about this. There was a JPL Ghost Conference in August of 1976. Why do I call it a Ghost Conference? Well, Lou knows, and he's already grinning. There was a study that was done, and it's mentioned that in a conference on missions beyond the solar system organized by L.D. Friedman and held at the Jet Propulsion Laboratory of August 1976, the idea of a precursor mission out beyond the planets of the solar system, but not nearly to another star, was suggested as a means of elucidating and solving the engineering problems that would be faced with in an interstellar mission. Now, the interesting thing is that Lou doesn't remember having run this. I have talked with people at the JPL library. I have talked with Marcia Neugebauer. I've talked with Ed Stone. I've talked with Alex Dessler. I've talked with a variety of other people, and no one anywhere remembers this conference. And the organizers were up there in years at the time and have passed on. And this is actually from the paper that was published in Icarus. And this is Leonard Jaffe and Charles Ivey, and Jaffe passed away some years ago. Jaffe was an interesting guy. He was actually at JPL and was the mission scientist for the Surveyor missions that soft landed on the moon. And Charles Ivey, I do not know about, and some of the older people at JPL may or may not know of him. I don't know if he's still around or not. But again, this was talking about a mission out of the planetary system, launched about the year 2000, looking at low-energy cosmic rays, interplanetary gas, mass of the solar system. Secondary objectives include the investigation of Pluto, because it turned out that Pluto was in about the right point at the sky at that time. And they noted that for a year 2000 launch, the Pluto encounter and orbiter can be included. So at least, and again, people were thinking about this. Now it turns out this actually came out of a study that was held a little bit earlier, which is indeed online. It's documented in JPL Publications 77-70, and it's about 113 pages long, and it's an incredible tour de force of what sort of things that one might want to think about doing science, about what one could do about propulsion, about all of the idiotic details that one would have to worry about really flying such a mission. One of the more interesting things I thought that was brought up in this was an idea that had been kicked around for some time about, okay, so can I build a cryogenic spacecraft in order to try to take my operating temperatures down, in order to try to conserve electronics temperatures, in order to try to conserve power, to try to extend the life of the electronics. So it was interesting, very much a thought idea about what you could do. This study was actually run in study was actually begun in November of 1976, about 2 months after the Ghost Conference, which supposedly, according to this report, was the inspiration for it, Lou. And this report actually was published on the 30th of October, 1977, less than 2 months after the Voyager 1 launch, which I think is another interesting point. Propulsion was the issue, no surprise there, and nuclear electric propulsion, it turns out, was actually the baseline for what could be done because it was obvious that that was the right thing to do. Well, then you flash forward a little bit to 1987, the question of large NEP systems. Well, we can go large. There was a thing called the 1,000 AU mission, TAU, which was actually laid out here at JPL. Not quite here, but close. Nuclear electric, go to 1,000 astronomical units in 50 years. Simple power supply, needed 1 megawatt of electricity. I'm going to have a 60 metric ton launch mass. I need 40 metric tons of liquid xenon. Now, I should mention that the current worldwide production rate of liquid xenon these days is about 35 metric tons. So it was an interesting and very ambitious project. Now, the real interesting number is that in order for the engineering design to close, I needed a specific mass of about 12.5 kilograms per kilowatt. That is, if I look at the power supply, the power plant, that's what it has to weigh for every kilowatt I put out. And that has been the big bugaboo, to use a technical term, in nuclear electric propulsion. Flash forward, if you look at what happened with Prometheus and you include the obnoxious radiators, because I have to get rid of waste heat that I don't use. I have structure that I have to carry along. Prometheus, depending upon how you do the calculation, ended up at about 80 kilograms per kilowatt. Most spacecraft that you can look at that are doing some sort of solar electric propulsion end up at about 60 kilograms per kilowatt. If you look at the book, Ion Propulsion for Spaceflight, that Stillinger wrote back in the 60s, because he did literally write the book on ion propulsion, he said you can do all these wonderful things in the solar system if you can get the specific mass down to about 30 kilograms per kilowatt. And we've never been able to get there, and we've beaten on that and beaten on that and beaten on that. And the problem has been that nuclear electric propulsion has always been too intrinsically heavy, not because of the power supply, but because of what I have to do with the converters and have to get rid of the waste heat. Well, anyway, that's the large size. You can think about going back to smaller ideas. There was a NASA Interstellar Probe Science and Technology Definition Team, or IPSTDT, as we do with acronyms. This was stood up in 1999 to re-look at the whole problem. And the idea here was to use solar sails because, you know, you wanted to be able to get out fast. Solar sails have been talked about. Sonder and Tsiolkovsky had actually come up with the idea of solar sails, again, talking back in the 1920s. There's some materials issues, there's some engineering issues, but nonetheless, they baseline this. The idea is to make this work. You could, at least on paper, perhaps get to 200 AU in 15 years, which would be great. Payload requirements similar to those of Pioneer 10. You're talking about 25 kilograms, 20 watts of power more or less. A spacecraft at about 250 kilograms. And the idea is that you'd have to go in close to the sun, turn the solar cell full into the face of the sun, and then that would enable you to basically to turn off gravity and go zooming out of the system. And it sounds great. There's some issues with it, and I'm hoping that in the context of the workshop this week we can perhaps talk about some of those. So again, the problem really is with all of this that all these approaches need propulsion development. They need something. And every time that this has come up in the context of a decadal survey, this mission has already been pushed off because advanced technology is needed. And this has been going on now for about 20 years. We did a study looking at, under the NEP Institute for Advanced Concepts back in 2004 for a launch in February 2019. I don't think we're going to make that. About 12 kilograms of science. That was about a metric ton. In the middle is a photograph of, this is the 1980 idea that was in the context of the Jaffe and Ivey paper. This is with the 2015 departure. 30 kilograms of science, and the whole thing weighed about 11 metric tons. You can see the Pluto spacecraft hung off the bottom. And then finally the solar sail, and again I mentioned about that, which would take a sail which would be let go about at the orbit of Jupiter. There have been other things that have been looked at. There's a thing called radioisotope electric propulsion. This was an idea about, well, if I've got, you know, if life gives me lemons, make lemonade. That is, if I've got a lot of radioisotope power supplies that I have to run, need to run the spacecraft anyway, let me hook some of them up to a small ion thruster and do some extra thrusting once I'm out of the sun's gravitational field. And actually there's a way, at least again on paper, that one might put that to advantage. The question again is the mass of the power supply. The solar sail implementation, this was looked at in some detail by the people over at ESA. They looked at various prototypes of how that one might unfurl the sail with a big emphasis on the structure and how that you would deal with that, because again, there's some fairly non-trivial engineering that goes into that. If you look back at the spacecraft that we've got now escaping the solar system, and again, these were discussed, It's interesting because they're all dominated by the high gain antenna. The real problem is I have to figure out how the devil to get the information back. And so the Pioneer 10 and 11, New Horizons, the Voyagers, IIE is, again, this was a concept that was studied for NASA that we did under the Vision Mission program. And the interesting thing, I talk to people and they say, well, you just use the laser comm system, what's the problem? And it turns out that the problem is that I can't really point a spacecraft that well. If you want to use a laser comm, I can get the size of the downlink down to about the size of the Earth, and that's great because now I have to figure out how to keep the spacecraft stable. I have to figure out how to point it. If I'm far enough away, I can't do this closed loop, so I have to have a really good ephemeris on board or I will never hear from the spacecraft again. Lots of interesting problems. If basically we looked and took a look at this sort of thing, and I could do a great job with laser comm if I can get the pointing down to a little bit less than about a micro radian or so. And first time I brought that up to some of the systems engineers, they finally quit laughing after about 15 minutes and told me what the problem was if I didn't have a guidance system that was about the size of the Hubble Space Telescope. All of these concepts that have been discussed have actually got a pretty good set of instruments. The interesting thing to look at is what we've done with instruments and sort of what the payload mass fraction is. Typically, these things run about 10 to, well, about 7% up to maybe 15. Actually, Ulysses, which of course was an all fields and particles mission, did a really good job with the instruments. They didn't have to worry about the silly cameras. And so they were actually able to pack more instrumentation in as a function of the overall spacecraft dry mass, about 16%. But the problem always has been these contenders about, how do you deal with technology readiness against flight time? I mean, there's some things that we could do now, but we don't get out that fast. Solar sails have held the interesting possibility of going a lot faster, but there's some development issues, as I say, and I think we're going to be talking about some of those this week. One of the things that you can look at are the launch vehicles. For all these various missions, these have been big. These photographs are actually about all to scale as best as I could do with PowerPoint. You see an Ares 5, well, that's gone away, of course, but the SLS is about the same size, we're talking about now, about the same size as the Saturn V. And one can think about using really big, dumb launch vehicles once again to at least try to get things out of the solar system rapidly. Certainly, if enablers for any of these architectures, you need to have the launch vehicle, you need to have the power supplies, I need to have the DSN, and oh, by the way, somebody's got to pay for the mission ops and data analysis. Although, given what we've been able to do with Voyager these days, I think one can get that down to a reasonable level. One of the things that we looked at in the Vision mission with REP was trying to put together some sort of mission, looking at what you could do in the latter half of, in the rest of the 21st century with various gravity assist. Basically, the thing that works is putting on an upper stage and using Jupiter, and so once every 12 years, you've got a launch window going out to the right place in the solar system. This is a concept of using an Ares 5. You can see the little bitty thing up there that's the spacecraft on top of this huge thing. We were actually able to find out that you could actually get a launch of something like about a C3 of 300 kilometers squared per second squared, which is about twice the launch energy of New Horizons, which means about 4 times the speed, which means here to lunar orbit in about 2.5 hours. So it would be a pretty impressive thing to do. And you can look at nuclear stage. I mean, as long as you're doing paper studies, why not pull out all of the stops? The interesting thing is, this shows what these are some various ideas about heliospheric speed you could get to. The notch that's there has to do with what you can get from a Jupiter gravity assist, and then if you can put in some more acceleration outside of Jupiter, again, that's a way with say, like a radioisotope power supply, you can get your speed up, and that ends up giving you transit times. We estimated somewhere between about 22 and 38 years to get out to 200 AU, not the 15 everybody would like, but I claim I can build this without a lot of new technology development. So these things have been advocated for a long time. One of the things that the community has kept trying to do fairly successfully is keep them into the various NRC plans, the decadal plans, the NASA roadmaps. It is a thankless task, but nevertheless one that is necessary. And I would contend that it's just a question of how and when. Solar sails may still have a role in this. The SLS may have a role in this. One of the problems that the Human Exploration Mission Operations Directorate has right now at NASA is they need to have some way of keeping the assembly line open, and I keep telling them, look, give the Heliophysics Division one of these things and we'll be glad to make use of it for you. Just don't send us the bill. And I just wanted to note the background I've been using on the slides, well, nice photo of Alpha Centauri and Beta Centauri, and one can still dream. Thank you.